Okay, so this is problem 2.20 out of Griffiths' Introduction to Quantum Mechanics. Before I get into solving this problem, I just would like to ask if you wouldn't mind please liking the video and subscribing to my channel. It's an easy and free way to support me, and I post a lot of different videos with solutions to problems out of common undergraduate physics textbooks. So if you're somebody studying physics or just interested in physics, I think my YouTube channel would be really good for you. Okay, let's get into the problem now. So we have a free particle which has this initial wave function. We're asked to normalize our wave function, find phi of k, construct psi x of t in the form of an integral, and look at some limiting cases for large and small a. So part A is pretty straightforward. To normalize a, we're just going to do the integral of the modulus squared of our wave function. In this case, it'll be minus 2a, the absolute value of x, dx, equal to 1. That's just how we normalize our wave function. Now we can simplify this integral a little bit. If you look at this function, and if you note that it's equal to, obviously, f of minus x, because the absolute value will take care of any negative sign, then we recognize this as an even function. And since it's on some even interval, in other words, minus a to a, this case you can think of it as being minus infinity to positive infinity, but this works for any from minus a to a. We can write this then as 2 times that same integral, except now we're going from 0 to infinity. Dx equals 1. And this one is pretty doable. You can do a u substitution here. We'll let u equal minus 2ax, and du equals minus, I did not want to do text mode. I never use text mode. I hate when that comes up. Minus 2a dx. And then from here you can see dx is minus 1 over 2a du. You could put this into an integral calculator if you'd like, but it's so easy. It's probably quicker to do this than turn on your laptop, load everything up, and do that. So now we're going to do our substitution. Our bounds, if we were to do u of 0, plugging in 0, it's still 0. But if we were to plug in infinity into that, this goes to actually minus infinity. So u of 0 is equal to 0. Plus infinity goes to minus infinity. So note the sign change. We have a minus 1 over 2a from when we do our substitution, e to the u du. Now we can write this as, well, first off, clearly the 2's will cancel. So we have our constant, our normalization constant, a squared over little a. And the negative sign is going to be replaced because we're going to flip the bounds of our integral. I just wanted to write this step out. I was thinking about just doing the integral, but just so you can see what we're doing. This negative sign turns positive when we flip the bounds of the integral. Just making sure you're okay with that. I'm sure most of you are. I might be over-explaining, but I'd rather over-explain than under-explain. So this is obviously just e to the u. It's a pretty easy integral to do. Equals a if we multiply both sides. we have e to the 0 minus e to the minus infinity equals a. So this will be going to 0, it's decaying. This is just 1. So then clearly a is equal to the square root of little a. You're probably fine with that. We've done this a few times now. Now we want to do this in momentum space, which is what part B is saying. So what we're going to do is we're going to follow this formula. Our wave function in momentum space is the square root of 1 over 2 pi times the integral from minus infinity to positive infinity of our initial wave function times e to the minus I kx dx. This is equation 1.04 in the textbook. Well, pretty straightforward. We can just plug in. We know what a is, so we can plug this into our initial wave function. So let's just go ahead and do that. Our wave function then is the square root. I'll write it all over, square root a over 2 pi, the integral from minus infinity to positive infinity, e to the minus I absolute value x, e to the I kx dx. Now, the way that we're going to solve that is we're going to express this as, this should be a minus sign because that's in our equation. So we're going to use Euler's identity here. Cosine's even, so it's not affected by that. But then you'll get a minus I sine kx. So we're going to have all of this times e to the minus a absolute value x. And then we're going to distribute this. And we're going to get two integrals. So hopefully that makes sense. A over 2 pi. So our first integral will be minus infinity to positive infinity. E to the minus a absolute value of x. This is our cosine kx term. Dx minus I, the integral from minus infinity to positive infinity, e to the minus I absolute value x sine kx dx. Okay. So, a few things. We can simplify this a little bit. Hopefully you can see that this is an even function. We already made an argument for why the e term is even, and of course cosine is obviously always even. And an even function times an even function is an even function. On the other hand, e to the minus ix is even, but sine of kx is always odd. So we have an even function times an odd function, which is an odd function. This is odd. And again, we can apply this because it's on a bound from minus infinity to positive infinity. It could have been any in the form of minus a to a, but in this case it's infinity. This whole integral part is 0. Meanwhile, for the even part, we could utilize the exact same trick we used in the normalization constant, where it's 2 times the integral from 0 to infinity. So let's do that. So then our wave function, so this will now be 2a over pi square root the integral from 0 to infinity. And then we're just going to have e to the minus ax cosine kx dx. So this one would be maybe where you put things into an integral calculator or look it up. The solution for this will be, well, here I'll show you what I found. I have an integral table I looked up, and what I found was e to the ax cosine bx, which is the integral we have, is equal to e to the ax times a cosine bx plus b sine bx, all divided by a squared plus b squared, where our a is minus a and our b is k. So in our case we have 2a over pi square root times e to the minus ax times minus a cosine kx plus k sine kx all over a squared plus k squared, evaluated from 0 to infinity. So if you plug in infinity, you'll have e to the minus infinity, so it's going to go to 0. But if you do it to 1, our e to the 0 is just 1, and because that's our lower bound, there'll be a sign change, right? And this will be 0, and this will just be a. So 2a over pi square root times a over a squared plus k squared. Okay, so that is part B. Part C wants us to find psi in an integral form. So let's go to C. What we're going to use is this. Psi of xt is 1 over the square root of 2 pi. These are all just Fourier transforms of each other, but these are also just equations in the book. We can go from the momentum space to position space through these transformations, and this is equation 2.106, at least in my book of Griffiths. And honestly, it's pretty easy, because all that we really need to do is plug in to our plug this in, not there, plug into here, because we already found that. So we have 1 over square root 2 pi out here. We have a 2a over pi square root, the integral from minus infinity to positive infinity. I'm going to pull this a out, and then a squared over k squared, we're actually going to leave that inside the integral, because remember, we're integrating with respect to k here, so we can't just pull that out. We have to be a little bit careful. And just so you know, omega is equal to h bar k squared over 2m. I believe it is for the free particle. Well, that's all you can really do here, since it just wants it as an integral. Don't want to ask Siri anything. So if we take the limit as a goes to infinity for, I'm assuming, psi of k, that will be approximately, so we have 2a over pi still, square root times, what we're looking at here is the fact that k is really much less than a. So it's essentially a over a squared, which is 2 over a pi, square root, which is our approximate. I think this is the approximation that they're looking for. And then you can do the same thing as it approaches 0. In that case, you have 2a over pi square root times a over k squared. So in this time, what we're saying is that k is much greater than a. So that's why we did that one. And that this is approximately your psi of k. I think that's all it's looking for there. So that's how you do this problem. Hopefully it makes sense. If it did, please like the video and subscribe, and I'll continue to post more solutions out of this and other textbooks.